Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dogba Jr., your math tutor and an instructor of mathematics at the University of Liberia. In my today's lecture, I will be discussing differential equation. So under differential equation, I'll be looking at how we solve differential equation using variable separable method or separation of variables method. So under separation of variable method, I have like two different types that we experience when we are dealing with variable separable method. The first type has to do with the case wherein we can easily separate the variables. Just from the first look of the problem, we can easily separate the variables on separate side of the equations and integrate both sides to get the general solution. But what about cases that you cannot easily separate the variables from the first look of the problem? Where you have to bring in some substitution and find derivatives before you can be able to find the separable forms of the variable and find the general solution. So we want to look at the second type 2, that we call reducible to variable separable form. So if you have a problem and you notice that you can reduce that problem to variable separable form, then it means that it is under type 2. So let's look at a few examples. In previous lessons, we discussed a few problems. We solved problems before on the same method. So you can just practice. And we also solved a lot of problems on a variable separation method 1. So you can also practice as well. Please don't forget to subscribe to our channel. Okay, so we have question 31 and 32. So we want to look at these questions quickly. The first question says, sine inverse of dy by dx equals x plus y. Now, the first thing we need to do is to ensure that we get rid of this inverse and get rid of this dy by dx within the angle of this trigonometry function. So we know that sine inverse of sine of x is equal to x, or sine of sine inverse of x is equals to x. So our x here represents what is here. So therefore we can take sine on both sides. We take sine on this side as well, x plus y. So sine of sine inverse of dy by dx is just equals dy by dx. The next thing we need to do is to substitute. Now we cannot expand this thing right here, sine of x, cos of y, sine of y, cos of x. So we want to substitute this so that we just have a single variable so that we can easily separate the variables. So now we say let u or some other variable, it could be t or whatever, let u equals to x plus y. Then we differentiate both sides. Remember, now we have a new function u and the initial function y. So you have two functions, two dependent variables with a single independent variable x. So we're differentiating u du by dx. Differentiate x is just 1 because it is an independent variable. Plus derivative of y now is dy by dx. So the next thing we want to do is to find dy by dx. So we can just solve for dy by dx right here. Is equals dy by dx. Then we replace in the original problem. So we can replace now. We have dy by dx to be equal to du all over dx minus 1 or equals sine of x plus y, but x plus y is just u. So we can now separate the variables. So we can multiply all side by dx. So we have du, dx cancel. So this guy will go across. It's just equals to dx because dx times this is dx, so you go across. Dx times 1 is dx, you just go across. It becomes positive. Plus, and then sine of u dx. So we can factor out. So if we factor out now, we will just have 1 plus sine of u dx. That is dx into this 1 times dx into this one equals the sine of u. So because we have the x here and this expression is in u, we must divide it on both sides, 1 plus sine of u. Because we only need x right here as a factor, 1 plus sine of u. So this and this go out. So we have du over 1 plus sine of u equals to dx. Now we have separated the variables. We can integrate both sides. So to integrate the first integral, this one, we know that 1 minus sine square u is equal to cos square u, and 1 over cos square u is equal to secant square u. So if we make this to be 1 minus sine square u, we can replace it with cos square u. And then if this is cos square u, 1 all over cos square u is equal to secant square u. And we know that the integral of secant square u is just equal to tangent of u. So we can rationalize 1 plus cos or sine square u, or sine of u, we can rationalize it. So it's 1 all over 1 plus sine of u. To rationalize a two-term expression, it means you take the conjugate of it. That is 1 minus the opposite sign, 1 minus sine of u. 1 minus sine of u. So this is just du. And then equals dx. In fact, dx now is just x. The integral of dx is just x. Now you multiply this and this, it gives you 1 minus sine square u. So you can multiply 1 times 1, 1 times sine, sine times 1, sine times sine. It'll give you 1 minus sine square u du equals to x. So we have the integral of 1 all over, now this 1 minus sine square u is equal to cos square u. So we can say cos square u. So we say 1 all over cos square u du minus the integral of, so we took them separately, sine of u all over cos square u. So this cos square u can be written as cos of u times cos of u. So if you look at carefully, sine over cos is just equal to tangent, and then 1 over cos is equal to secant. So 1 over this is just secant square u du, and then sine over this is tangent of u, and this is secant of u du. So what is secant square u? The integral of secant square u, the integral of secant square u is just equal to tangent of u. So this is x plus y. So the integral of secant square u is just equals to tangent of u minus the integral of tangent of u secant of u, or secant of u tangent of u, is just equals to secant of u, or equals to x plus some arbitrary constant c. But what was u? U was just x plus y. Don't forget to replace u. X plus y is x plus c. So this is our general solution for the differential equation. Now let's look quickly at question number 32. So question 32, again, look here. If we cross multiply dy times x, dy times 2y, dy times 3, you're going to have a kind of long expression that you may not be able to separate the variable so easily. So based upon that, we want to substitute this entire expression, since it is not in terms of one variable, or it is not in the form that we can do factoring by grouping. So we can substitute that entire expression by some variable. So we say let u equals to x plus 2y minus 3. So that we just have a single variable right here. Now we differentiate both sides. The u equals, this is 1, this is 2. Then you attach the y by dx because y is a function, and plus 0. So the next thing we want to do is to find dy by dx. So we can multiply this whole thing by, we want to get rid of this by 1 over 2 and just send this 1 across. So this time this is du all over 2 dx. So this time this is 1 over 2. If we send it across, it becomes minus 1 over 2. This time this now becomes just dy by dx. So we have already solved for dy by dx. Now let's put it in. So dy by dx now is du all over 2 dx minus 1 over 2 is dy by dx equals 2 all over this entire thing is just u. So we can get rid of the denominators. So we find the LCD. So 2 u and dx. So that each of these denominators can go into this. So 2 dx go into this, 2 go out, dx go out. So you left with u. So it's u du minus, let's go into this, 2 and 2 cancel, you left with u dx equals, let's go into this, u and u cancel, you left with 4 dx. So we can send this term across and just factor. So if we send it across, we factor, it will be u plus 4 dx. Now what we need to do is to divide both sides by u plus 4 because this is x. So u plus 4. We don't need it there. So we have u over u plus 4 du equals dx. The variables now have been separated. We can integrate both sides. So for this one, we can use the long division. We divide this by this expression. Or since we don't want to use the long division, we can bring in some trick. So we know that u plus 4 minus 4 is the same as u plus 4. Now I use 4 because 4 is in the denominator. So if this was 3, I would have used u plus 3 minus 3, whatever, du. And then this is just equal to x. So I can rewrite this numerator such that I will have u plus 4 all over u plus 4 minus 4 all over u plus 4 du all equals to x. So this into itself one time, this into itself one time, you just have the integral of 1 du minus the integral of 4 all over u plus. Now this 4 can be written as 2 squared. This 4, I can bring this 4 outside. And I write this 4 as 2 squared. Sorry, it's just 4. Yes, I took it to be their tangent inverse property. So this is just equals to x. Now the integral of 1 du is just u. And then this is 4. This is a linear factor, so it just becomes u plus 4 all equals to x plus some arbitrary constant c. So we can bring in the value of u. So we know that from the problem u was x plus 2y minus 3. So we can replace x plus 2y minus 3 minus 4, the ln of x plus 2y minus 3 plus 4 equals to x plus c. Simplify, right? So this x will cancel this x. This 3 can go across. So you have 2y minus 4 the ln of x plus 2y plus 1 or equals to c plus 3. Now this c plus 3 is still a constant. So it's like saying a constant plus another constant is equal to a constant. So this whole thing will represent it by, say, some a, for example. Now we can have 2y equals, so we can just send it across. It will be positive 4 the ln of x plus 2y plus 2 plus a. So I can divide all sides as well by 2. So y will be 2 the ln of x plus 2y plus 2 plus, now a constant divided by a constant is equals to a constant. So this thing will just lead to a constant. So I just rewrite c, or I can use b or whatever letter I want to use. Now I can take this 2 and send this 2 to the power of this argument. So I have y equals to the ln of x plus 2y plus 2 raised to the power of 2 plus some arbitrary constancy. So there's a general solution of the second problem that we have. So thanks ever so much for watching. Please subscribe and see you in our next lecture. Thank you.